Hey math people, it's Mr. Ray here with our next lesson in grade 11 university math. We are finishing off the unit on functions and transformations. This lesson is on inverse of a function. So you've come across lots of inverse functions or inverse operations in the past in your math journey. Things like adding and subtracting, those are inverse operations. What an inverse operation does is it undoes the original operation. So if you added 3 to a number, if you subtracted 3 from the result of that, you would get back to the original number. If you multiplied by 2 and then divided by 2, you'd be back to where you started. So multiplying, dividing, those are inverse operations. Squaring and square root, those are also inverse operations. Even in trigonometry, grade 10, you saw the sine function and the sine inverse function. They also undo each other. So we're going to look at that inverse function more generally in terms of equations and graphs. Okay, so the formal definition, and I'll kind of elaborate on this with a nice picture. The inverse function of f is written as f, and then it looks like it's an exponent, f negative 1, but we would pronounce this as f inverse. I guess I should put a dash there, f inverse. That is not an exponent, and this is a common misconception, and it's unfortunate the way the mathematician that originally wrote this, it's not the same as 1 over f of x. That would be the reciprocal function. The function and its inverse property, the function and its inverse have the property that if you use the original function f and you put the input of a in and got the result b, well then if you took the inverse of f, the function that's inverse, and you put in the output from a, you would get back the original, if you put in the result of this f of a, if you put the result b into the inverse function, that would restore the original a value. So if you're kind of looking, just one sec. If you remember when we talked about function notation, and we had this magic box, which was a function called f, and the input comes in, we'll call it x for now, and x, the function f does something to it, and the output is f of x. Okay, so that's just basic function notation. So if beside it we had this other box, and we made this function the inverse of f, so we'll call it f inverse. If we fed this back in, so if we fed f of x back into the f inverse function, we would get back x. So in this inverse, the input's coming from the bottom and going out the top. In the original function f, inputs coming in here, outputs coming out the bottom. So it's sort of like a circle. It just kind of does something to x, and then, the function f does something to x. You get f of x, the result of that. And if you feed that result back into the inverse function, f inverse, you get back the original x that you started with. Okay, so that's really what an inverse function does. Okay, and like we've said, we can write it as f inverse of x. Again, we pronounce it, we use of x, and we pronounce the negative 1 as f inverse. F inverse of x. This is f of x. Okay, now there's all sorts of different characteristics of inverse functions. We're going to cover a few of those. Now, the inverse of a function can be found by interchanging the x and y coordinates of the function. So if you had a table of values, we'll go back to our little picture here. If you had a table of values for, we'll call this x and f of x, I'm just going to make up some values here. So if I had 0, 1, 2, 3, and the output was 17, 21, 31, 54, just a totally random function. So if that's what the table of values of this f inverse function, what happens is when you define you have a table of values for f inverse of x. So if I had x here and f inverse of x here, okay, what happens? These are like your x and y values, as always. What happens with these tables, if this is the original function, this is the inverse, what happens is your x values from the original function become your y values here, so 0, 1, 2, 3, and your output values from f become your input values for the f inverse of x. So your table of values might look something like this. So you can always create some points on your inverse function if you know some points on your original function just by interchanging the x and y values, switching x and y's. Okay, so we're going to do that here. There's one other point here. We'll talk about this when we do example on the next page. Sometimes the inverse of a function is not a function itself. And we're going to test that the exact same way we would test a regular function. It is a regular function. So the vertical line test, if we see a graph of the inverse function, we can test if that inverse function is in fact a function also. Okay. Now here we have, it's sort of like what we just did. We've got a set of ordered pairs, like a table of values for the function f. So we've got our x and f of x points. Now these are the only points that are on this function. This is not like a continuous line. These aren't just a sample. So when we actually plot these, we're not going to pretend that we know how they're connected. We're just going to draw the points themselves. We call this a discrete function, which it's not a continuous curve or line. It's just discrete points on the graph. Okay. So just like I showed you on the previous, on my blank page. So if I wanted to do a table of x and f inverse of x, okay, all we're doing is like we did before, we just flip the positions of these on our table of values. So our x values would be 0, 2, 5, 6, 7, and they're related back to the x coordinates. The inputs on this table are now our outputs. So -5, -4, -3, -2, and 0. Okay, so that's nothing new that I didn't just show you. Now we're going to actually plot this, and there's going to be a characteristic of this as well. So first of all, I'm just going to plot my original function f points. So I'll start off with -5, 0, -4, 2, -3, 5, -2, 6, and 0, 7, which unfortunately it's a little bit off the graph, but let's just pretend the graph's a little bit taller. Okay. Now the interesting characteristic before I actually draw these points is if you draw, and it's related back here, the graph of f inverse of x is the graph of f of x reflected in the line y equals x. So this is kind of a different reflection than we're used to with transformations. The reflections we did there were vertical and horizontal, so either reflected in the x or the y-axis. These reflections are reflected in this, basically a slope of one graph through the origin. So I'm just going to draw like a dashed line here. This is the line y equals x. Okay, and I'll put that up here. So once I draw my other points for the inverse function, you're going to see how the original points and the inverse points are related to this line. So let's go ahead and plot these. So 0, -5 is down here. 2, -4. 5, -3. 6, -2. And 7, 0. So we got the same number of points. And if you kind of looked at this without knowing about this line y equals x, you wouldn't think too much of it. But if we actually connected these, so I'm going to connect each point to its inverse point. So -5, 0 to 0, -5. If I just do a light line between them, and I do the same thing for these other points that are related to each other. Once I take this ruler away, you'll see what the situation is. Okay, so some of these are a little bit hidden just because of the axes. But what you can see here is there is a reflection of the original points to the inverse points. And the reflection this time, it's a little bit harder to see unless you draw this line. But this point here is reflected, and by reflected, it's basically an image. It's a reflection right across this line, so it's exactly the same distance from this line y equals x on both sides. So that distance there is the same as that distance there, etc. Actually, that line isn't very good. Should be going through the origin. So let me try that again. Yeah, I think it's because these aren't to scale. So let me try to do a little bit of justice there. Anyways, these points are equidistant, meaning the same distance from this reflection line. And that's one of the characteristics of the inverse. Not only are you flipping the x and y coordinates, but when you plot the points, they're mirror points across this line y equals x. Now we wanted to do a domain and range of f of x. Yeah, that's not all that interesting, but the domain of f of x. Now, it's not x is any real number, it's only these values here. So you can see that x equals these 5 values here. I'll put them in ascending order at -5, -4, -3, -2, and 0. And the range, again, it's not all the real numbers, it's just these integers here. F of x or y is equal to 0, 2, 5, 6, 7. Okay, and then if I do the same thing for the inverse function, so there's f, here's the inverse. This time the domain is, if I look down here, 0, 2, 5, 6, 7. And then the range is, I guess I got to call it f inverse of x this time, is equal to -5, -4, -3, -2, and 0. Okay, and if you compare these, there's another characteristic, which shouldn't be a big surprise. The domain of the original function is the range of the inverse function. So these two are equal, the same, and these two are the same. So the domain, like I said, domain of the original function is equal to the range of the inverse, and the range of the original function is equal to the domain of the inverse function. And that should be fairly obvious based on the fact that we're just flipping x and y values. Okay, so there's, and just to add a little something here, f inverse of x is a reflection of f of x. Across y equals x. the line y equals x. There you go. Okay, so that's what happens when you graph a function and its inverse. I know this function and its inverse were just a collection of points, but it's kind of easier to see when you just have specific points as to how those points relate to each other. Okay, so let's do another example. Two more examples. What we're going to do here is we're actually going to determine the new equation. We weren't dealing with equations in the first example, just a table of values and graphs that came out of that. So in this case here, we've got two equations. So what do we want to do? We're going to determine the actual equation of the function, of the inverse function. Then we're going to graph both f of x and its inverse, and then determine whether the inverse is also a function. I talked about that earlier because it's not always a given. Sometimes a function meets all of the requirements of a function, but the inverse does not. So we're going to start with f of x equals 2x minus 3. So this is the process you're going to do, especially if it's linear. This is obviously a linear equation. So the first thing we're going to do is we're kind of revert back to our old ways. We're going to change f of x to the actual coordinate that it represents, which is the y. Okay, and we're going to do that because we're going to now flip the x and the y in the equation. So I'm going to draw a line here, and you'll see why in a sec. So now we're actually going to flip. So the y becomes x, and the x becomes y. Okay, now the reason for this line, as soon as I did that flip, well, above the line is f of x, the original equation, and below the line, once we flipped, that's the inverse, f inverse of x. So now what we want to do is basically isolate this for y. We're going to rearrange this equation so we have y equals something. So the first thing we're going to do is add 3 to both sides. So I'm going to have x plus 3 is equal to 2y. And I'm getting close to having y isolated, but I need to divide everything by 2. So I'll just show that here. Divide each term by 2. And then I now have the y isolated here. I'm going to switch sides, put it over here. So x divided by 2, that's the same as 1/2 x. And then we had 3 divided by 2, we'll just leave it as a fraction. So this is the equation of the inverse. To make it formal, using function notation, we'll change the y at this point back to f inverse of x. And then the right side is still the same. So this is the official inverse function in function notation. Okay, now what we're going to do is graph each of these equations. So the original function, y equals 2x minus 3. So if you remember how to graph your linear, you're going to start with the y-intercept, because that's the point that's kind of given to you, and then we're going to have a slope of 2. So we go right 1 up 2, right 1 up 2, etc. Keep following that pattern. So those are 3 more points. So I'm going to put a line through there. So this is that's f of x. I don't have to draw the whole thing since I've already got its definition given here. And then the second equation, it's also linear, so the inverse function. So I'll do the same thing I did. We're going to start with the y-intercept, which is 3.5, which is 1.5. And then the slope this time is, you can see it's actually the reciprocal of 2. So that means we're going to go right 2 and up 1. So that's there, right 2 up 1 there. So I've got 3 points there. I'll just make my line. So this line is our inverse function of f inverse of x. Okay, and if I drew my y equals x here, you'd see that these two lines are actually a reflection of each other in the line y equals x. So I won't do that here, but you definitely could. And you notice where the inverse and the original function join is where their x and y values are actually the same. And that makes sense because if you switched x and y, but they were at the same to begin with, well, that must mean that the inverse and its original function must have the same point there. So anytime the two functions cross, you know that the x and y value where they cross is the same. Okay, the last thing we're asked to do here was determine whether the inverse f inverse of x is a function, and it's not too hard to tell if you did your vertical line test of this line here. That's definitely a function. So in this case, we can state yes, f inverse of x is a function. And because we had the graph here, we could use the vertical line test for that. Okay, so that's how you would find the inverse of any linear function. You do the exact same process, obviously. First of all, write the f of x as a y, then flip the two x and y's, and then solve, rearrange for y, put back into function notation. But this time you've got the inverse, and that's how it's done. This equation here, this obviously is a quadratic. Now, there's a slightly different thing we have to do. So we will do what we did up here, change the f of x to y. Okay, and again, the next thing we will do is flip the values. Actually, no, let's change that up a bit. Before we flip the values, one of the things we have to do if we're finding the inverse of a quadratic, because it's going to be really hard to isolate. If I change the x's to y's, it's going to be super hard to isolate for y. So what we're going to do, and this takes you back to your grade 10 day, so hopefully you remember this skill, we need to change this quadratic equation, which is in standard form. We want to change it into a vertex form. So I'll put a little box here, change to vertex form. That's key. So obviously if it's given in vertex form, you don't have to convert it because it's already there, but if it's standard, you have to do this in order to find its inverse. So if you remember, first thing we do is we isolate, put brackets around the first two terms, and then factor out the a value there. So we're going to have 2x squared plus 8x plus 29. Okay, and then what we have to complete the square here. So we take half of the 8, which is 4, we square it, and we're going to add and subtract that value inside the brackets. X squared plus 8x plus 16 minus 16, bracket plus 29. And then we want to get rid of the negative 16 that we had to put there to keep the equation balanced. So remember, in order to take that out, I have to check to see if there's a factor outside the brackets, and there is a factor of 2. So before I can take this outside the brackets, I have to multiply it by 2. That's exactly what we're going to do. So it's now moving outside, and I have plus 29 minus 32, because that negative 16 times 2 is negative 32. Okay, at this point, we can finish off our vertex form. So we're going to create this as a perfect square trinomial now. We're going to change it into a binomial squared, and then we're just going to combine those two terms. That's a minus 3. So if you remember, the way we get this converted into a binomial squared is we take, obviously that's going to be an x, and the second term inside here is half of this value here of positive 8, so that's a plus 4, And now we successfully have this written in vertex form. Now I'll explain why we did that. So if you notice now, I have one y value and one x value. So, and that's the beautiful thing about vertex form. Prior to this, I had, on the right side, I had an x squared and an x value. But when you change to vertex form, you just have an x. And now that we have that, I am now going to switch the variables around. So above this line, just like the linear conversion, up to this point, we're working with f of x. And now we're going to switch the x and the y. So this is going to be x equals 2y plus 4 squared minus 3. So as soon as we did that, we're now dealing with the inverse function. But we want to put it in a way that's, we've got the y, we can isolate for the y, just like we did here, and then change it back to function notation for the inverse. So this one's a little trickier because, we've got a squared there, and we've got a subtraction and an subtraction and a multiply. So you have to think about, peeling the onion. If I want to get x isolated, the first thing I have to do is add 3 to both sides. So that's what I'll do. And that leaves me with 2y plus 4 squared. The next thing I do, the next outside layer that I need to do is divide everything by 2. So when I do that, I get x plus 3 over 2 is equal to y plus 4 squared. And now we're actually going to take the square root of both sides. So square root of x plus 3 over 2 is equal to y plus 4. But there's an important thing we have to do here. When I take the square root of that, it just removes the squaring. But when I take the square root of this, you have to remember, for example, if I asked you what the square root of 16 was, the actual answer is plus or minus 4. So over here, I really should be putting a plus or minus. Okay, and then the last thing I do is subtract 4. So when I do that, I've got my minus 4 plus or minus x plus 3 over 2 is equal to y. And now I can change this, I'll just write it over here. I can change that y to the inverse, f inverse of x is equal to negative 4 plus or minus square root of x plus 3 over 2. Yeah, and that's it. So here is your actual equation of the inverse function. And it does look fairly complicated compared to the linear. And you can see instead of, it's no longer a quadratic equation, it's actually going to be a square root function. Okay. Now, when I do the graphs, okay, well, I can look at the vertex form of this, and I can actually pull out the vertex. The vertex of this is negative 4, 3. So I can put that there. I can then grab a few points. For example, I can't really put the y-intercept of 29. It's just too big for the graph. But I do know that this is our a value here, which means it's got a stretch factor of 2. So I can look at where the points would have been and then multiply that difference by 2. So I'm not going to get into quadratics here, but those would be 2 points, 1 to the right, 1 to the left, and 2 up. And then I have another point at negative 2, 5, and its mirror point over here at negative 6, 5. So I now have enough points. I can do a fairly decent parabola. You can see it's pretty far away from intersecting the y-axis at this point, which we kind of knew because it actually crosses at 29. Okay, so there's the original graph f of x. Now, what I could do, rather than plug some points in here and I could actually do what I did on the first example, and that's take my points that I know here and then just flip the x and y coordinates. So this point here, -4, -3, on the inverse, that point would be -3, -4. So that would be down right here. And if I did have my graph of y equals x, you can see that those 2 points are, equidistant across that line y equals x. I'll also do, okay, let's do this point. That point is -5, -1. So when I change it, that becomes -1, -5, which is down here. And this point here is -3, -1. So that's -1, -3. And then finally, these 2 points, this first one is, well, this point is -6, 5, so it becomes 5, -6. So all the way down here. And then the other point would be 5, -2. Okay, now if I actually did this, and the shape should be the same, just kind of turned sideways, so I don't have to really guess too much about what this would look like. So it's basically a parabola turned on its side. Now, you probably guessed just by the points that I graphed on this. You can see that, well, if I was applying the vertical line test, I've actually drawn 2 sets of points that violate the vertical line test, plus an infinite number of other ones that would also violate, because vertical line test crosses 2 everywhere except for this pseudo vertex down here. Now that's because, so basically if I drew it like this, you would say, well, that the inverse is not a function. But what we do sometimes with the inverse of a quadratic function is this plus or minus that I talked about here. If I just chose one of those, for example, if I just chose the plus, so if I change this to f inverse of x equals -4 plus, and then the same thing here, x plus 3 over 2. If I just use that branch, it would only be these points here. So the upper branch of this parabola on the side. If I just chose that one branch, it would be a function. So that's usually what we do for inverse of quadratic functions. And by the way, if you haven't guessed it already, the inverse of a quadratic function is a root function. So this, you can see that, it's right in the equation. But this looks an awful lot like the square root based function that was over here. And you remember when we drew that, we only drew this top branch. I didn't really explain at the time that there's really 2 branches. We just drew that function as this, because if we didn't, it wouldn't be a function if we had points down here as well. So, so the explanation of this, I don't know if I have enough room here. The inverse of a quadratic function is not a function. Try to squeeze this in here. Unless we limit it to the upper branch. Only, and that's really the plus sign in the equation. Okay, and so what we did is by putting this in here, that limits this graph to just this part here, and therefore it passes vertical line test, therefore it is a function. Okay, if I wrote it like this, I would have to declare this is not really a function. It fails the vertical line test, but that's what we do for these root functions in order to allow them to be classified as a function. Okay, so you basically have a procedure now where you could take any linear function and find its equation of its inverse function, or if you had a quadratic function, how to change that into its inverse function. This one was definitely more tricky, especially considering we had to start with standard form, change it to vertex form, and then begin our work to convert. Obviously, if you're given the equation in this form, vertex form, it would be half the amount of work, because all you have to do is switch x and y and then try to isolate for y. You'd still have the issue all the time with this plus or minus, double branch. So in the future, if you have a test question, if you're going from here to here, you can just write the plus sign here. Okay, I would like you to have both to show me that you realize there's two possible values here. But when you write it as a function, you have my permission to eliminate the minus sign in the plus minus part. So it looks like this. Okay, so that's it for this unit. We've covered quite a bit of ground talking about functions. I mean, that's the name of this course. We talked about what a function is. How do you determine if it's a function? We learned about domain range. We learned about function notation. We learned about 5 base functions, 2 of which you've done before, 3 of which you haven't. How to apply transformations to any of those. And then finally, well, we also learned how to graph any transformations very quickly using base point transformations. And then finally, in this lesson, we learned about what's an inverse function, what are some of the characteristics of an inverse function, and how do you graph an inverse function, how do you find the equation of an inverse function if you're dealing with linear quadratic. We're not going to have any questions where any of these original functions are anything other than linear quadratic, so don't worry about that. You just have to know these 2 processes. Okay, so that's it for this unit, and we'll see you at the beginning of the next unit. Take care.